All right, so on the page from yesterday, I just wanted to give you a couple hints for numbers 11 on the other side, okay, and through 15. So on this page, if you can flip it back to where we were kind of working through the different examples, right? So yesterday we basically ran through an example of each type of calculation. That's what you guys have on your own paper. I encouraged you to write it on a separate sheet of paper. And that way you can attach it to this, and when you turn it in, I'll give it back to you on Thursday, and we'll kind of go from there. So your goal is you are turning this in today, okay? So with this, if you weren't here yesterday, I did record what we went over, and I made it little segments. So they're all like little 4-minute video clips of everything that we did yesterday. And so you can just watch the ones that you actually need. And that goes for everybody who was here yesterday too. You guys can just go back and just watch whatever example that you needed. But trying to find one that is blank. So I will just use this one. All right. So we're going to talk about number 11. Before we totally dive into it, though, just wanted to remind you of what we did right in our notes on Friday. We wrote down this little piece with the expectation that we were going to come right back to it yesterday, and then I kind of changed it a little bit on you. So molar volume, what we said on Friday was that it is liters per mole. This is only for gases, and it's specifically you have to be at standard temperature pressure, STP. If you are not at that, then you have to use the ideal gas law in order to calculate for whatever volume it is, okay, and things like that. But if we are at STP, we get to use this conversion, which is no different than us saying grams per mole. All right, so it's a conversion factor, or particles per mole, like Avogadro's number, right? So 22.4 liters per 1 mole. It's only for gases. Don't try to use it for liquids. All right, so then in our notes, we used an example to kind of make sure that we got the point across. And so we have our balanced equation, and I said, how many liters at STP will 5 grams of oxygen produce, right? And we probably had a different example. I think I changed the example all day, so you might have a different number. But whole idea here is that you are just running a stoichiometry calculation. So just like when we were learning about stoichiometry, we brought words down to the right. We made a conversion from grams into moles, brought words down to the right. Then we crossed the mole bridge, or the mole ratio, which is coefficients. And then we bring words down to the right. This is the new part that we can use that gas conversion now. Moles to liters is going to be that 22.4 liters for every 1 mole. As long as we're at STP, we can use that. So the part that I wanted to kind of emphasize or re-emphasize was we had also included an example of, I believe, a liter to liter. You guys might have had this. So we'll rewrite this right now. We're going to do that with number 11, all right? But big idea with liter to liter calculations, we are assuming we can go ahead and assume a mole to mole. And what it comes down to is that you have 22.4. That's going to show up at the top of this calculation as well as on the bottom, which means you have 22.4 divided by 22.4, which is just the number 1. So we're going to end up getting rid of both of those. So it's just going to be a liters straight into mole to mole ratio, which gets our answer in liters. All right. So, I mean, if you're thinking about the dimensional analysis part, yeah, we're kind of getting rid of the part where it looks exactly like what it's supposed to look like. But this is the shortcut that I do encourage you to use, especially for number 11. So looking at number 11, we basically have the scenario of Here you go. When hydrogen burns, water vapor is produced. So the equation is 2 hydrogens plus some oxygen gives us 2 moles of water. So if 6 liters of oxygen are consumed, what volume of water vapor is produced? All right, so the fact that we are starting with the 6.0 liters and we are going to volume tells us it's that liter to liter conversion, okay? We do have our balanced equation up there. I'm just going to rewrite it so that I can just kind of scooch the page up, okay? And we are going from 6 liters of oxygen to question mark liters of water vapor. And that's our problem right now. All right, so running through this, okay, we have 6.0 liters of oxygen. Okay, so in a typical stoichiometry, so you can choose to either watch this part or you can be writing this part down. I'm going to be writing it all out just to get rid of it, and I'll show you the shorter part right after, all right? But I would definitely be paying attention to that. So we're going to bring words down to the right. I have liters of oxygen right here. And remember, no matter what, if I'm trying to figure out something that's across any balanced equation, we have to go through that mole. We have to convert to the mole. That's the only way you can relate things in a balanced chemical equation. So we have moles of oxygen right there. That's going to be our conversion. Okay, and I'm so sorry I forgot to put at STP. Okay, it's very important that it said that. Okay, so our conversion going from, actually no, I'll say that for the end. I'm going to bring words again down to the right. Okay, so now that we're in moles, right, we cross that bridge, right? Once we make it to mole time, we have to cross that mole ratio, mole bridge, right? So now we're going to have coefficients. And that's going to be where we change into whatever we are looking for. So we were at oxygen. Now we need to be in water. And that'll be where coefficients are going to go. Okay, and I'm going to bring my words down to the right. And we're going to finish off with a conversion again. So we're going to have moles, and then I'll have liters of water because that's what it's asking for us to solve for. So now filling stuff in, if these are both just conversions, remember all of our conversions are always based around the number 1, right? So those were our 2 guaranteed ones. The liters is going to be that conversion. How do we convert from moles to liters? And that would be with that number 22.4, right? Over here, moles to liters, that's that 22.4. Okay, so then our coefficients here, what are we going to put with H2O on top? A 2. And what are we going to put with oxygen? A 1. Okay, so we could type all that into our calculator just like we did back in stoichiometry days, right? But the part that I wanted to kind of reiterate was that, okay, we have 22 these are identical. They are like mirror images of each other, right? So we have this divided by that, and that can all go away, as in we don't need to include that. We can show that the liter amount is related by their mole ratio. That's really what it is. All right, it comes down to that mole ratio. So really what you guys can have written down is this. 6 liters of O2, and then we can just relate it to 1 mole O2 for every 2 moles of H2O tells me that the answer is how many liters? What's the answer to this right here? What? Not quite. Almost. Other way. 12. Yep, you're good. All right, so 12 moles, 12 liters of water. Okay. All right, so we got it? And that's kind of how to shorten that up. Okay, so that was what I wanted to show you for number 11. All right. So I'm going to scooch this out of the way. Number 13, 12 was what I meant. Sorry. Can't count, apparently. So number 12. Number 12 is pretty much like the one that we wrote in our notes on Friday, so I'm not going to re-go over this, but I will give you the little hint. Just looking at the setup. The setup is already there for you, okay? So you already know that you're going to start with a number that's given to you in the problem. We have our guaranteed 1 right here, our guaranteed 1 on the end. What that tells you is that this is a conversion to liters. This is a conversion to mass. So 22.4 molar mass. Okay? And then this one in the middle is going to be our coefficients, your mole ratio. Okay? Number 13 is not stoichiometry. Number 13 is a conversion. It's just a conversion, which means that we're really going to focus on the fact that we have the ones. That's how you convert things, right? So you're going to have 1 mole. You're going to match it up to what does that equal in liters. 1 mole, what does that equal in grams? So again, molar mass, 22.4 is the direction you want to go with that. And remember, you're multiplying across the top. Okay, there's nothing that goes under this first one. Okay, so you multiply across the top, divide by the ones across the bottom. Okay. All right. Next one would be number 14. Okay, so number 14 was based off Dalton's law, and so we took some time to really do that one, especially in our lab, right? So it was the idea that atmospheric pressure is always equal to your water vapor pressure plus whatever pressure of gas. So if you remember from the lab that we did with the sinks, right, we were trying to figure out what was the pressure of the butane. Well, this question, number 13, is asking you to, I'm sorry, I'm so off on my numbers. Number 14 is asking you to solve for what is the mass of the hydrogen gas. Okay, so what is the pressure of the hydrogen gas? Can't read either. So you're using the whole idea of atmospheric pressure has to equal both your water vapor pressure plus pressure of your gas. And that's who you're solving for, pressure of the gas. Which means, are you adding in this one? You're going to subtract, yep. And the water vapor pressure is given to you, so you don't need to use the table, but just so you know, that's where that number came from, right? The 2.72 kPa, it's like coming from one of these tables, okay? All right, and last but not least, number 15, which I thought when I added it to this page, I thought it was going to be like the one that you had to use PV equals nRT to get all their individual pressures. But if you read this question with me very, very carefully, it says 1 liter container filled with oxygen gas to a pressure of 0.12 atm at 0 degrees Celsius. So 1 liter, we have a pressure 0 degrees Celsius. Another 1 liter container is filled with nitrogen for a pressure of 0.12 atm and 0 degrees Celsius. Is anything really changing besides just who the gas is? No, basically all of our variables are remaining consistent, right? So then it says the gas samples are now going to be combined into a 1 liter container, meaning we're not opening it up and saying, oh, now it's 2 liter, because then nothing would really happen necessarily, right? What we're saying is that now we're just going to pour them both into one container and seal it off, and it's 1 liter. What do you predict the pressure is going to do? Should go up, right? Shouldn't there be a whole lot more particles hitting the walls if we combine 2 containers of particles, right? Does that make sense? So this one is actually as easy as it looks. What do you think we're doing if this is Dalton's law? You add them. Yep. You're going to add them together. That's it. You could already tell me what the answer is. Huh? Yep. Yep, you got it. So Dalton's law says pressure total is equal to pressure 1 plus pressure 2 plus pressure 3, ... right? This one only has 2 pressures. Add them together. And that's it. So meaning you don't need to use a temperature. You do not need to use the volume. We're just relying on the fact that those are staying consistent. Okay? So that's all I've got for you for this part. So once again, your goal is to complete this. Don't worry about doing anything over here on the right-hand side. You're gonna leave that blank, okay? And then you've got this side. As far as the coloring goes, if you have time to color it nicely, then do it. If you don't, if you have kind of a stack of missing work that you need to have taken care of, then feel free to get the right color and do a squiggly. Just show me that you put the color in the right spot. That would be fine with me, all right? You do have to show me your work, so make sure along the way you're showing me your work. If you put it into your journal, be ready to snap a picture and email that to me, okay? All right, so that's kind of all I've got. You guys have kind of the remainder of the period to get this done and work on it.